Hello and welcome to 2.6, which is where we're going to be looking at limits as x approaches infinity and how that relates to horizontal asymptotes. So we've already looked at if x is approaching a specific number and your y value approaches infinity or negative infinity, we know that that results in a vertical asymptote. So where we would see a horizontal asymptote is if x is approaching infinity or negative infinity and your y value approaches a specific number. So if I think about this graphically, okay, this should make some sense. Okay? If I take a look at this, if I look at the limit as x approaches infinity of the function, my y values will get closer and closer to my horizontal asymptote, which would be at 0. Similarly, if I look at limit as x is approaching negative infinity, if I head off to the left forever, fx, I also would have that my y values are approaching 0. So if either of these are true, it doesn't have to be both, but this tells me that I have a horizontal asymptote at y equals 0. Okay? So where you might see one where it doesn't approach both is something like this. Okay? This one I have the limit as x approaches infinity of f of x equals, I'm just going to call this L. Okay? But my limit as x approaches negative infinity of f of x is equal to negative infinity. Okay? So this part here tells me that I have a horizontal asymptote at this y value. Okay? So that's 2 or 5 or whatever that's at. The other piece tells me that as x goes on forever, so does y. We say that this means that our function is decreasing without bound. It's going down forever and never stopping. If it was going up forever and never stopping, it had no final destination, that would be increasing without bound. So this one, we say that f of x decreases without bound. And it won't, you won't usually find a question that actually asks you to state that. It's more if you had a question that says f of x is decreasing without bound, you would know what that means. It means it's going to go down forever, okay, somewhere. And you would look at what x is approaching to determine which direction. That's how, okay? So formally stated, a line y equals L is a horizontal asymptote of a function if f of x approaches L or y approaches L as x approaches plus or minus infinity. So for example, if I have this guy, I can see where my horizontal asymptote is, but if I actually find the limit as x approaches infinity of f of x, I'll see that this equals -3. This would therefore, because x is approaching infinity and I converge on a final value, this tells me I have a horizontal asymptote at x equals -3. If I take a look at the limit as x approaches negative infinity, we see that as I head to the left forever, my graph goes up forever. It approaches positive infinity. So this would be one where we increase without bound. Okay, again, we would pay attention to where is x approaching to tell us which direction we're increasing forever. So like a parabola, get a parabola opening up like this. This would both have a limit as x approaches infinity equaling infinity and a limit as x approaches negative infinity equaling infinity. So it would actually increase without bound in both directions. Or if we had an upside down parabola, it would be decreasing without bound. Okay. Now the problem is, what if we don't have a graph? Okay. Again, we would want to figure out, does this converge on a specific value? If I take a look at this, basically what I'm doing is I'm saying, okay, I have 1 over infinity minus 2. Okay. Infinity is a very large number. If I subtract 2 from that, it doesn't really make much of a difference. I take 1 and I divide it by a very, 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 very large number. What is that going to equal? As I make that bottom number larger and larger, what y value am I approaching? If I take 1 and I divide it by a million and then a billion and then a trillion, I'm going to keep getting closer and closer to 0. So this is actually equal to 0. Okay? This would be a horizontal asymptote. That means at y equals 0. Didn't ask us for that, but now the problem becomes something like that is nice and simple. Now, what if I have a bunch of x's? Okay? Effectively, what I'm saying is I've got infinity squared plus 3, infinity cubed minus 2 times infinity plus 4. How am I supposed to determine what this is approaching? There's two ways you can think about this. One is the formal way they show you in the textbook, and another way is a bit more intuitive for most people. Again, depending on how you're proceeding with your coursework, if you're going to university and taking this with a professor, it's really going to depend on how picky they are. So go to your lectures. So if I take a look at this, basically what I'm trying to figure out is what's going to happen as I plug in infinity and these numbers grow and grow and grow. Okay? And one technique we have is actually manipulating this a bit by multiplying by something equivalent to 1 so that I can determine which values will stop mattering as infinity gets plugged into these values. So what I'm going to do is, because my highest power is x cubed, I'm going to multiply the top by 1 over x cubed, and I'm going to multiply the bottom by 1 over x cubed. This is then going to give me the limit as x approaches infinity of x squared over x cubed, which would give me 1 over x, plus 3 over x cubed on the top. On the bottom, I'm going to have 1 minus 2 over x squared plus 4 over x cubed. The reason I'm doing this is because if I keep plugging in big, 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 big numbers, we just determined 1 over infinity approaches 0. Well, if I have 1 over infinity here, 3 over infinity cubed here, 4 over infinity cubed here, and 2 over infinity squared here, these are all going to approach 0 as x approaches infinity. And what I end up with, therefore, is on the top, 0 plus 0 over 1 minus 0 plus 0, or 0 over 1, or 0. Okay. Now, for some people, they find this a bit hard to look at because of the 1 over x cubed, and they're like, that doesn't intuitively make a lot of sense. So here's the more intuitive way. I've got the limit as x approaches infinity of x squared plus 3 over x cubed minus 2x plus 4. If I plug in 100, on the top I have 100 squared plus 3. On the bottom I have 100 cubed minus 2 times 100 plus 4. The bigger I make that number, once I'm up to 1,000, a million, a billion, a trillion, that bottom part is going to grow way faster than the top part, because x cubed or a billion cubed or a trillion cubed is way bigger than billion squared or a trillion squared. So effectively, on the top, what happens is as I approach infinity, the 3 doesn't really matter. If I take a trillion squared and add 3, doesn't make a lot of difference to me. So the top is essentially behaving just like the x squared. On the bottom, similarly, if I take a trillion and I cube it, if I subtract 2 times a trillion plus 4, again, that's not making a lot of difference to my overall number. These numbers are just too large. So the bottom is behaving like x cubed. Well, I can simplify that to be 1 over x. And again, I know if I take 1 and I divide it by a very, very, very large number, this is equal to 0. It approaches 0. My y value approaches 0 as x approaches infinity. So effectively, if you have a rational, the top will behave like the highest power. The bottom will behave like the highest power if x is approaching infinity or negative infinity. So for most of these, they're fairly intuitive like this one in the sense where like I have a highest power and things just cancel out and I can get an actual number answer. Where these become a bit more difficult is like our back page, where you have something like a radical, especially if you are approaching negative infinity. So I will show you both methods here. Okay. So if I do the multiply by the highest power method, my highest power is an x squared, but it's actually 1 over root x squared. Okay. Once I do that, I have the limit as x approaches negative infinity. On the top, I end up with root 1 plus 5 over x squared. On the bottom, I end up with x over root x squared minus 2 over root x squared. So right away, we can see a couple things that are going to approach zero. This guy's going to approach zero, and this guy's going to approach zero. So now what I have is the limit as x approaches negative infinity of root 1, which is 1, over x over root x squared. Now, a lot of you are thinking, hey, root x squared is just x. So what I'm going to do is, well, this is just equal to 1 over x, which is equal to 1 over 1, which is 1. The problem with that is we're approaching negative infinity. We cannot say this. Really what's happening is actually that I've got the limit as x approaches negative infinity. I've got the 1 on the top. But on the bottom, when we plug negative infinity in here, we would get negative infinity. When we plug negative infinity in here, we get positive infinity. So on the bottom, we actually have negative 1, not the positive 1 we think. This is then equal to negative 1. So you just need to be very careful if you have a radical and you're approaching negative infinity, be very careful with your sign. You want to approach it the other way. We would have limit as x approaches negative infinity of root x squared plus 5 over x minus 2. So if I look at the highest power on the top, my highest power is root x squared. My highest power on the bottom is x. Again, a lot of people will say, well, look, that's equal to x over x, which is 1. No, it is not. Because if I plug negative infinity in on the top I have an x that is always positive. And on the bottom, I have just plain old x. Okay, so if I plug negative infinity in on the top, negative infinity in on the top is going to give me a positive number. Negative infinity in on the bottom gives me a negative number of the same magnitude, which gives me negative 1. Okay, so yes, you have an x on the top and the bottom, but x on the top is always positive, and that x on the bottom is going to end up being negative. So just be very careful. You're approaching infinity from the negative side, negative infinity, and you have a radical.